I had some questions about number 13 and 14, and so I wanted to take a look at those. Lots of good things here. Remember, the big idea is creating right triangles within three-dimensional shapes. So we're going to see lots of Pythagorean triples come back. I don't think we have any angle measures here, so I don't think we're going to see 45, 40, or 30, 60, 90 triangles here. Obviously, we'll see lots of Pythagorean theorem as well. All right, first one, CH is equal to 7. So make sure you've got a good drawing. Make sure you're labeling it. This is very visual. You need to be able to see this stuff. CH is 17. Okay, so we've got a diagonal that's cutting through right here. That's 17. GH has a length of 8. There that is. FG has a length of 6. And for the first part here, I want to find the length of AG, which is the diagonal of the solid. Remember, to find the diagonal of the solid, you need the full dimensions of the solid. So we've got a length, we've got a width, we need the height of the solid, okay? One of the strategies that I really push, and I don't remember if it came up in one of the lessons I put online, but really important in general with these problems, when you're working with three-dimensional shapes, you need to simplify the pictures in a lot of cases. And so, for example, I'll pull out one face and just look at that. So I'm noticing here that I have a lot of information about this face right here, okay? That face is a rectangle, okay? And that rectangle has a base length of 8, and it has a diagonal length of 17. And then what you realize is this shape right here is a right triangle, okay? I should be able to use either the Pythagorean theorem or triples. And you notice in this case, it's a Pythagorean triple. It's an 8, 15, 17 triangle. So again, I can't stress, if you don't know those triples, you forgot them over spring break, you need to get those memorized. 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, and then there are other ones, 9, 40, 41, 11, 60, 61, 20, 21, 29. There are other ones, but those four are the big ones that I really pushed in the last couple of sections. Make sure you know those. So anyway, the height here is 17, height is 15, and we have that information. So they want me to find the length of AG. AG, of course, is just the diagonal of the entire solid, and so AG is going to cut back through here, and again, it's all about making a right triangle. Okay, so you can create a right triangle kind of on the inside like this. Hopefully everybody can see that. I didn't draw it super well, but we've got the right triangle there. Okay, the height of this thing is 15, so that means AE back here is also going to have a length of 15. Okay, notice this side of that right triangle is a diagonal of the base. So once again, always a good idea to draw faces separately so you can kind of figure out what's going on. So I'm going to draw that base. It's a rectangular base. It's got a length of 6 and 8. Okay, it's not drawn to scale, but you get the idea. I need the diagonal across like this. Okay, and once again, if this is 8, this length over here is going to be 8. You've got a little 6, 8, 10 right triangle. Okay, so we've got sides of 15 and 10. Okay, and again, can't stress it enough, draw pictures separately. You've got that right triangle on the inside now, and you've got a height of 15, and you've got a length of 10, and at that point you can use the Pythagorean theorem and find AG. I will let you finish that. Do make sure you simplify the radical. We go on to part B here, and we've got different measurements. So let me take some of this stuff out of my diagram, see if I can save my diagram. And they give us a new set of measurements that I will put up here. All right, they tell me that AG has a length of 50. Oh, I should have left AG in there. Okay. AG is right here. It has a length of 50. It says that AE has a length of 40. All right. It says that EF has a length of 3. And it wants me to find the length of FG. Okay, I'm actually going to put that triangle back in that I had before, because if you notice something, I have a right triangle here with a hypotenuse of 50 and a height of 40. That's coming from a little 3, 4, 5 right triangle pattern. 3, 4, 5 multiplied by 10. So it's going to be 30, 40, 50, and we've got the diagonal of the base. Okay, remember, we're looking for the length of FG, all right? Draw that base separately. What do we know about the base? We know it's got a height of 3, and we know the diagonal is 30. Okay, so at this point, you should be able to use the Pythagorean theorem. 3 squared plus x squared is equal to 30 squared. And again, I'll let you simplify it down from there. It's in the back of the book, so you can check your answer as well. All right, let's look over here at number 14 and see what's going on with that one. This is a pyramid, and they tell me that the length of PR is the slant height. It's the height of this pyramid. Slant height is 10. The diagonal of the base is 12 radical 2. Okay, and I'm not going to draw that in the picture because it's going to kind of gum up my picture, but here's the key. This is a square pyramid, okay? So the diagonal is 12 radical 2 here. If that's a square pyramid, remember squares divide into 45, 45, 90 triangles. Remember that from when we investigated the 45, 45, 90 patterns. And so since that's a little 45, 45, 90 right triangle, I mean, you could make that an x and that an x, and you could say x squared plus x squared is equal to 12 radical 2 squared. You could do the Pythagorean theorem and get a solution, but we don't need to. It's 45, 45, 90 triangle, so 12, 12, 12 radical 2. The base dimensions are each 12, okay? Does that tell me anything? Yes, that tells me ID. ID is 12, okay? We want the altitude, okay? Well, notice we've got a right triangle right here, okay? This is going to the center, so if the whole side is 12, we know that that side is going to be 6. And check it out, right triangle with a side of 6 and a hypotenuse of 10. This is a 6, 8, 10. It's coming from a 3, 4, 5 right triangle pattern. So I love Pythagorean triples. They're so wonderful, save you so much time when you're given a triple. Let's look at RD. Okay, RD is right here. RD is just half the length of the side, so RD is going to have a length of 6. And then finally, PD. Oh, we are going to have a little bit of work there on PD. Notice something. We have another right triangle right here, okay? We have that triangular face, and that should be a right triangle. I'm going to erase some of this work here. So to find PD here, if I draw this face of the triangle, PAD, okay, and we draw this in, we know that whole length is 12, we know this length is 6, we know that length is 10, okay? We're looking for PD, which is along here, okay? That's just a little right triangle. That's an altitude of a right triangle, the slant height. Be careful here. You might get in a hurry and say, ooh, look, I see a 6 and a 10 on a right triangle. But notice, in a 6, 8, 10 triangle, the 10 would be the hypotenuse. And the 10 is a leg, okay? Remember, the hypotenuse is always opposite the right angle. So you're actually going to have to do 6 squared plus 10 squared and take the square root of that. It's going to be the square root of 136. I think 136 is divisible by 4. I'm guessing that's all you're going to be able to get out of it, but you'll need to break that radical down. So hope that helped on number 13 and 14.